This is your presenter, Asloob Mudassar, and I am presenting slide number 9A of the course on atomic and molecular physics. The topics that will be covered today are quantum mechanics of hydrogen atom, motion in a central field, azimuthal part of hydrogen wave function, Legendre polynomial, spherical harmonics. Quantum mechanics of hydrogen atom, motion in a central field. Here I shall solve the Schrodinger equation for hydrogen atom, assuming a general central potential represented by V as a function of R, which is symmetric with respect to the center, that is with respect to the nucleus center. In such a potential, angular momentum of a particle is conserved. So you see that this is the important property that is connected with the central potential, that is the angular momentum of a particle is conserved as established in Kepler's laws of areas for the motion of a planet in a solar system. Classically speaking, orbital angular momentum as a function of time is constant provided V of R is the central potential. In quantum mechanics, the angular momentum represented by L hat. So you see that in quantum mechanics, all these variables will be represented by the operators. So this is L operator, that is the angular momentum will act as an operator, and we shall put a hat over here. So there will be other operators in quantum mechanics, but I shall not be talking about again and again that these are L hat or L operator. Just I shall talk about the variables, and if you find a hat over there on such variables, you should assume that these are the quantum mechanical operators. So in quantum mechanics, the angular momentum L and the energy H are simultaneously measurable. That is L and H commute. That is the commutator of L and H is equal to 0. When we say that the commutator of L and H is equal to 0, which means that L times H is equal to H times L. And if you expand this commutator, you will write this commutator in the expanded form as L into H minus H into L. That is equal to 0. And since that is equal to 0, it means that L times H is equal to H times L. That is L and H commute. So when they commute, it means that they are simultaneously measurable. That is, both L and H can be measured simultaneously on a single measurement, So this is equation number 9.1. The components of L which are represented by Lx, Ly, Lz of the angular momentum L are not simultaneously measurable. And you know that these components that I have mentioned, that Lx, Ly, Lz, these are mutually not simultaneously measurable. That is, their commutator are not equal to 0, which are explained in equation number 9.2a, 9.2b, and 9.2c. In 9.2a, we have the commutator of Lx and Ly, which is equal to iota h bar times Lz. The next in equation number 9.2b, we have the commutator of Ly and Lz, that is equal to iota h bar Lx. And in equation number 9.2c, I have the commutator Lz times Lz comma Lx, and the commutator of Lz and Lx is equal to iota h bar times Ly. So these are the three commutators that are commonly used. You can remember them in the cyclic fashion, that is Lx, Ly give you Lz, Ly, Lz give you Lx, and Lz, Lx will give you Ly. So you can draw Lx, Ly, and Lz in a circular path, and then you can follow these very easily. So you need to attach iota h bar as an output element with each of these output operators. The components of Lj, where J stands for X, Y, and Z. So it means that I am talking about the three components Lx, Ly, Lz, and the L square operator are simultaneously measurable. that is L square and Lj, the commutator of these two quantities, these two operators is equal to 0. That is the commute, that is the L square and Lj, that is L square commute with components of the orbital angular momentum. And here J again stands for x, y, and z, but one at a time. So this is equation number 9.3. For a central potential, the following two commutators also hold. That is Lz and H commute as given in equation number 9.4a, and L square and H also commute as given by in equation number 9.4b. The commutator results in equation number 9.4, that is 9.4a and 9.4b, do not provide any new physical insight because their physical insight is covered with the previous commutators. So we may not need these commutators in our calculations because they don't provide any new physical insight. In both mechanics, that is in classical mechanics and quantum mechanics, the total energy H, the z component of the angular momentum, and the square of the angular momentum can be measured simultaneously to any desired accuracy. So these three quantities which commute with each other, so you see that these quantities can be measured simultaneously to any desired accuracy. A common eigenfunction is thus required for all these three operators, that is for the H operator, Lz operator, and L square operator. So you see that we need a common eigenfunction for all these operators. Due to the central potential, the nature of the problem has a spherical symmetry, and a spherical polar coordinates system will thus be used. In the diagram, you can see that I have drawn a geometry that is used to derive the connection between that is used to derive the spherical polar coordinates to be connected with the Cartesian coordinates. And you see that I have the three axes labeled as x-axis, y-axis, and z-axis. And you notice that there is a sphere centered at the origin of these coordinates. And I have shown a patch. The radial vector of a point on that patch is represented by the r, and the angle of the vector r with the z-axis is represented by theta, and the projection of r on the xy plane makes an angle phi with the x-axis. So you see that phi can have a value from 0 to 2 pi, and theta can have a value from 0 to pi by 2. Let us express the kinetic energy operator in spherical polar coordinates. You know that on the left hand side I have the kinetic energy operator, which is minus h bar square over 2 m naught into delta square. This is del square. So on the left hand side we have the kinetic energy operator minus h bar square over 2 m naught times del square, where m naught is the mass of the electron, h bar is the reduced Planck's constant. And on the right hand side, this is equal to minus h bar square over 2 m naught times 1 over r square times partial derivative of r with respect to r, and within the parentheses I have r square times the partial derivative with respect to r plus 1 over 2 m naught r square, and then multiplied with the L square operator. So you see that this is the kinetic energy operator represented in spherical polar coordinates. But you know that I have L square operator on at the rightmost end of equation number 9.5, which can be represented by equation number 9.6, that is L square is equal to L square operator is equal to minus h bar square, and within the square brackets I have 1 over sine theta times curly partial derivative with respect to theta, and within the parentheses I have sine of theta multiplied by the partial derivative with respect to theta, and then plus 1 over sine square times double derivative with respect to phi square. So I have curly square over curly phi square, that is the double derivative of with respect to curly over curly phi as shown in equation number 9.6. So you see that I have the kinetic energy expression over here in the form of the quantum mechanical operator. As V of R depends only on R, it is reasonable to separate the radial and the angular functions as given. Since in our problem, that is in the hydrogen atom problem, the central potential V of R depends only upon the value of R. So it is required that we can split the wave function, which is the psi of R theta phi, into two parts as the radial part and the azimuthal part. The radial part is represented by capital R, which is of course a function of R, and the azimuthal part is represented by capital F, which is a function of two variables theta and phi. The time-independent Schrödinger equation has the following form: H psi on the left-hand side, and on the right-hand side I have E psi. So H psi, H is a operator, Hamiltonian operator, operating on the wave function psi, and on the rightmost side we have E as the eigenfunction, and again the wave function. So E psi, so where capital E is the eigenvalue of this problem. And you see that in between these two, I have replaced H by its operator form, which is the kinetic energy plus the potential energy. So the kinetic energy is represented in its operator form, which is equal to minus h bar square over 2m naught times del square plus V of R. So V of R is the potential energy, and the minus h square over 2m naught del square is the kinetic energy. This kinetic energy expression has been given in equation number 9.5 and 9.6. So 9.5 and 9.6 give a complete description of the kinetic energy operator. So this Hamiltonian is actually the kinetic energy plus the potential energy of the problem. And you see that equation number 9.8 is actually the time-independent Schrödinger equation. We have to solve this equation so that we can get some useful information. Now you see that I am going to plug in the value of the wave function. And the wave function is given in equation number 9.7, which has two parts, the radial part and the azimuthal part, that is capital R and capital F. So if you plug in this value in equation number 9.8, that is on the right hand side of equation number 9.8, because we have to simplify the right hand side. So what we need to do is that you plug in that value over here, that is in the middle part. So you can put the value of psi from equation number 9.7 in the middle part and also on the right hand side part. So I am not using h square, and then I am using its operator form, that is the kinetic energy plus the potential energy. So you see that when you put the value of psi, so in the first term, you see that in the green, I have shown f as a function of theta and phi on the leftmost side, because this bracket, the square bracket, contains the radial part information. So f of theta and phi will be independent of the radial part, and the radial operator will not operate on that quantity. So I have taken the azimuthal part on the left hand side of this square bracket, whereas capital R, which depends upon the radial part, will be operated by the operator in the square bracket. So I have kept the radial part capital R shown in green on the right hand side of the square bracket. Now you see that once I have done is that, then of course there is one quantity which is in equation number 9.5, which is 1 over 2m naught r square into L square. And you know that here again since I have substituted my psi wave function, psi will also appear over here in the multiplication. And when psi will appear over here, so what I have to do is that I have taken capital R, which is the radial part, on the left hand side of this quantity shown in red, and the azimuthal part of the wave function is on the right hand side of the L square operator. Because the L square operator, you know that will operate has a is defined as azimuthal wave function. So L square, you know that it has a form given in equation number 9.6, which contains theta and phi derivatives. So it means that that is the azimuthal part of the wave function will be kept on the right hand side of the L square operator, whereas the radial part shown in red will be kept on the right hand side, will be kept on the left hand side of the L square operator. So I have shown the wave function in green and also the wave function in red, which explains that which part of the wave function will be operated by which operator. And on the right hand side of equation number 9.9, I have the energy, which is the eigenvalue of the problem, multiplied by the r of r, multiplied by the wave function, which has two parts, r of r and f of theta and phi. So simply speaking, that the radial part r and the azimuthal part f. So you see that this is now the differential equation. That is the Schrodinger independent, time independent wave equation, that if we solve, we can get useful information of the problem. That is, we are talking about the central potential problem, which is the potential used in hydrogen atom. So it means that we are actually going to solve the hydrogen atom problem. Psi is an eigenfunction of Lz, L square, and H. Here we are talking about the two operators, L square operator. So you see that when L square will operate on the azimuthal part of the wave function, which is f of theta and phi, I shall get the eigenvalue as h bar square omega. And of course, then on the right hand side, I have the azimuthal part as shown in equation number 9.10. So you see that here h bar square omega is actually the eigenvalue of this operator. That is the L square operator. When operating on the azimuthal part will give you the eigenvalue h bar square omega, and then of course the eigenfunction on the right hand side. And in equation number 11, you see that the Lz operator will operate on the azimuthal part, will give you h bar m as the eigenvalue, and then of course the wave function f as f. So you see that here I have shown only two operators operating on the azimuthal part, and I have shown their eigenvalues. L square operator has an eigenvalue h bar square omega, and Lz has an eigenvalue h bar m when they operate on the wave function f. So you see that this here I have assumed that these are the eigenfunctions, that is h bar square omega and h bar m are respectively the eigenvalues of the L square operator and Lz operator when they operate on the azimuthal part of the wave function. So you see that actually we have to find these eigenvalues in detail. H bar square, you know that is the reduced Planck's constant. So what is omega in equation number 10? So we have to find out the value of omega, and you see that in equation number 11 I have h bar m. So h bar is known. What is m? M is to be known. So we have to find the value of m over here. So here we have assumed, so equation number 10 and 11 are the total assumptions. And if we find out the value of omega and m, we can plug in those values over here, and then we can have this problem solved. That is L square operator on the azimuthal part and Lz operator operating on the azimuthal part of the wave function will be completely known. So in the next few pages, I shall be discussing how to find out omega and how to find out m and how to find out these and how to relate these two quantities also. Where h bar square omega and h bar m are the eigenvalues in arbitrary form corresponding to the operators L square and Lz respectively. M will be referred to as the magnetic quantum number. So you see that here m is unknown. We don't know that omega and m are the quantum numbers or not. We shall explore them in greater detail in the next few pages. But you see that same here I have given m the name the magnetic quantum number. And later we shall find out this. But here, for the time being, bear with me that m is actually the magnetic quantum number. Now you see that equation number 10 and equation number 9. We can use these two equations and dividing the resulting equation by f of theta. So I am using equation number 10 into equation number 9. And the equation number 9 is shown over here. This is equation number 9. So you see that I have in equation number 9 contains the term L square operator operating on f, where f is shown in red. So it means that I can substitute my value, that is L square f, from equation number 10, which is shown over here. So you see that I can use equation number 10 to replace the quantity L square operating on f in equation number 9.9. So this is what I am going to describe over here. So using equation number 10 into equation number 9 and dividing the resulting operator equation by f of theta and phi, the following equation can be written. So you see that I have now this equation. What I have done in equation number 9 is that I have substituted the value of equation number 10 in equation number 9 at this position, and then I have divided the both sides of this equation by the azimuthal part of the wave function, that is by f. So doing these two operations will give me the equation as shown in 10, as shown in equation number 12, that is in equation number 9.12. So I have minus h bar square over 2m times 1 over I square times the partial derivative with respect to r operating on r square times a partial derivative with respect to r plus v of r, which is the central potential, plus h bar square omega shown in red divided by 2m not r square, and this whole bracket is operating on the radial part of the wave function, and then on the right hand side we have e times r, or capital R, which is the radial wave function. So you see that equation number 12 contains only the radial part of the wave function, because we have eliminated the azimuthal part of the wave function using equation number 9.10. And you see that in this equation I have shown h bar square omega in red, and of course this quantity is unknown, that is omega in equation number 9.12 is an unknown quantity. So if we know the value of omega, we can plug in the value of omega over here, and then we shall be able to solve the radial part of this equation. And this equation, that is the equation number 9.12, will be solved in the next part of this slide, that is in slide number 9b. And here I am just solving the full effort that I shall make on solving, on finding the value of omega and also the value of m given in equation number 11, and also some rules and regulations related with omega and m, which I have called the m, I have referred to it as the magnetic quantum number. So let's proceed further, because now I am putting my efforts in order to find out the value of omega and the value of m, as these two quantities are shown in equation number 10 and in equation number 11. This is the radial part of the Schrodinger equation, in which h bar square omega is unknown. So equation number 9.10 will be solved first. That is equation number 9.10. So if we solve this equation, then we would be able to find out the value of omega. So it means that before we solve the radial part of the equation of the problem, let's first of all solve equation number 9.10. And I have written this equation as in equation number 9 as equation number 9.13. So L square operating on FLM will give you h bar square omega L FLM. So you see that here what I am doing with the equation number 10 is that I am dropping the explicit dependence of f on the theta and phi. So you see that in equation number 13 I am not writing theta and phi, because once it is understood that f is the azimuthal part of the wave function, it is obvious that it depends upon the value of theta and phi. So I am not writing it again and again. But you see that I have used two variables as a subscript with f, which is the azimuthal part of the problem. And the two variables are L, M, and small l and small m. And I have also used a variable as a subscript with omega, which is small l. Later on, we shall find out, we have to find out L and M in this problem, and of course omega L. Using our previous knowledge on the atomic physics, or on the advanced knowledge of the atomic physics, we have used L, M, M. L and M as a subscript with F, and L with as a subscript with omega. And now our objective is to find out L, M, and omega L. Now you see that I can show L square operator which is on the left hand side in equation number 13, I have the L square operator. This L square operator will be represented as Lx square, Lx square plus Lx square operator plus Ly square operator plus Lz square operator. Or simply, if I drop the word operator, I shall be saying Lx square plus Ly square plus Lz square operating on the angular part of the wave function, which is FLM, will give you h bar square omega L, and of course FLM on the right hand side, as shown in equation number 14. Rewriting equation number 9.14 as, so you see that I have moved the term which is a Lz square term on the right hand side as shown in equation number 15. So in equation number 14, I have moved one term which is Lz square on the right hand side. So you can see in equation number 15 this transformation. Now I have the two operators on the left hand side, which is Lx square plus Ly square, and on the right hand side I have Lz square. So now let me find out when Lz square will operate on FLM, what I shall get, which is explained over here. So Lz square operating on FLM will give you, I can split Lz square operator into two parts, Lz times Lz, and one of the Lz will operate on FLM. So when this Lz will operate on FLM, I shall get the result as h bar m times FLM. And you see that this is what I have used equation number 11 over here. So when Lz will operate on F, you will get the eigenvalue h bar m. So this is what I have done over here. So Lz will operate on FLM and will give you the eigenvalue h bar m. Now h bar can be taken outside the parenthesis, and the Lz operator on the left can be moved inside the parenthesis, which is shown over here. So I have h bar m, and the parenthesis contains Lz operating on FLM. And again, you see that when Lz operate, I have the eigenvalue which is h bar m and then FLM. So if you on the right, writing this in the form of equation number 9.16 will give you Lz square operating on FLM will give you h bar square m square times FLM. You know that these two quantities h bar m will multiply twice, and I have h bar square m square times FLM. Now you see that I have solved one of the operators from equation number 9.15. That is only when Lz square operator will operate on FLM. I have the solution of that one in the form of equation number 16. But still the other two operators are unknown, which I have expressed in the form of equation number 17. Using equation number 16 in equation number 15, I have this equation shown in equation number 17. So on the left hand side, I have Lx square plus Ly square in operator form operating on FLM, the azimuthal wave function, and will give you h bar square. And then I have omega L minus m square. And on the right hand side, I have again the wave function FLM. Now you see that my objective is to find out omega L, the value of m, magnetic quantum number m, and also the relationship between them. That is, what is the omega L minus m square stands for? What is this? So I have so next I have to solve and find out that is what is the omega L minus m square. So you see that in equation number 17 I am multiplying with the complex conjugate of the azimuthal part of the wave function FLM conjugate from the left hand side on both the equations. So you can see that I have on the next step is that I have operator which is F conjugate LM operating on the left hand side of equation number 17 from the left, and I have the same as a wave function operating the right hand side of equation number 17 from the left side. So you can see that the value of the complex F as F complex conjugate of F on the right hand side and also the complex conjugate of f on the left hand side of this equation, where it is obvious that I have multiplied equation number 17 by the complex conjugate of f from the left hand side on both equation on the both sides of the equation. Now you see that I can integrate this equation over the full space provided by the azimuthal variables, that is over the two variables theta and phi. So you can see that the double integrals with the full space operating over the full space provided by theta and phi on both sides of this one, and the quantity which was h bar square times omega l minus m square can be taken outside of the integral because this quantity is independent of the variable theta and phi. Now you see that it is obvious, since I have the double integral over the variables theta and phi over the full space provided by theta and phi on both sides of this integral, these two integrals you see that will give you a value which is always positive. So which implies that the quantity, this one, that is h bar square times parenthesis contains omega l minus m square, should also be at least greater than equal to 0. So you see that from this analysis, that is both integrals will be greater than 0. I am finding out this relationship that h bar square times omega l minus m square, this quantity is greater than equal to 0. Or I can drop out the h bar square parameter and I can simply write that omega l is greater than equal to m square, as shown in equation number 9.18, that is in equation number 18. So you see that this is the first relationship that I have found connecting the two unknowns. Omega l is greater than equal to m square. Now let's express lx square plus ly square as the product of l plus and l minus, where l plus is regarded as the creation operator and l minus will be regarded as the annihilation operator. Later we shall also see that l plus will be called as raising operator and l minus will be called as the lowering operator. Now we want to express lx square plus ly square in the form of the product of these two variables, these two operators, l plus operator and l minus operator, respectively called as creation and annihilation operator, or respectively called as the raising and the lowering operator, because when they will operate on a wave function, they will raise the wave function to its higher state, or when L minus 1 will operate on a wave function, it will produce a wave function corresponding to the lower state. So let's define L plus and L minus in equation number 19 and 20. So L plus is equal to Lx plus iota times Ly, and L minus is equal to Lx minus iota times Ly. And let's talk about these commutators, because now I have to find out some important result. That is, I want to have a relationship of Lx square plus Ly square in the form of the product of these two variables, that is L plus and L minus operators. For that one, I am using some commutators. So you see that the first is the after equation number 20, I have the commutator which is in the square bracket of Lz and Lx. And this commutator has been obtained from equation number 9.2c. And I have shown the expanded form of this commutator also. Lz times Lx minus Lx times Lz is equal to iota h bar Ly. So this is obtained from equation number 9.2c, and now I am referring this as equation number 9.21. The next commutator that I am using is Ly, the commutator of Ly and Lz. This commutator is obtained from equation number 9.2b, and its expanded form is Ly times Lz minus Lz times Ly is equal to iota h bar Lx. And I have relabeled that equation in as 9.22. That is the equation number 22. And you see that here I am multiplying equation number 22 on both sides by the variable minus iota, by the constant minus iota. So iota minus iota is being multiplied to both sides of equation number 9.22, and I shall get this relation. And the simplified version of this equation is shown in equation number 23. So I have iota times the commutator of Lz Ly is equal to iota times of Lz Ly minus Ly Lz, and on the right hand side I have h bar times Lx. Now you see that I have equation number 21 and 23 in front of you. So I am going to add equation number 21 and equation number 23, which will give me the following relationship. So you can see that I have added the left hand sides of equation number 21 and 23, and I have also added the corresponding right hand sides in the expanded form and also in the reduced form. And I have marked there a term in red and a term in blue because I am going to adjust these two terms. So you see that in the next step I have adjusted the red term. I have moved the red term somewhere, and also I have combined the blue term with some other term. And then you know that I have taken some quantities common from these parentheses. That is Lz was taken common on the left hand side of the first parenthesis, and Lz was common on the right hand side from the second parenthesis. And you know that these Lx plus iota times Ly is nothing but in the form of operator. If you write this operator, it is the operator L plus, and again minus Lx plus iota times Ly is again an operator which I have represented as L plus. You can see that I have defined L plus in the form of Lx plus iota times Ly in equation number 19, and similarly this will be used later, that L minus will be represented as Lx minus iota times Ly. So in the present equation I can use equation number 19. So you see that if you notice this, that Lz times Lx plus iota times Ly minus Lx plus iota Ly times Lz, actually this is the commutator of what? Commutator of Lz and Lx plus iota times Ly. So I can write this whole longer term into a commutator of Lz and Lx plus iota Ly. And on the right hand side I have h bar times Lx plus iota Ly. Now I can use equation number 9.21. Sorry, 9.19 shown over here, and I can replace Lx plus iota times Ly by the quantity L plus, which is the raising or the creation operator, which is you can see over here as shown in equation number 24 with red, that is it is a commutator of Lz and L plus is equal to h bar L plus. So you see that I have found this result. That is the result of the commutator of Lz and L plus. These two operators, the relationship, the commutator relationship of Lz and L plus is given as h bar L plus in equation number 24. I can similarly obtain but doing similarly performing such mathematical manipulations as shown for the equation number 24. I can also write equation number 25 directly as Lz, the commutator of Lz and L minus operator will give you minus h bar L minus. So without going without giving the detailed derivation, I have directly written that the commutator of Lz with the L minus operator will give you minus h bar times L minus as shown in equation number 25. Now combining equation number 24 and 25 gives me the following equation. So I can express equation number 24 and equation number 25 in the form of single equation. So I have the commutator of Lz with the L plus minus operator will give you plus minus H bar, and of course the operator L plus minus as shown in equation number 26. So when you choose plus sign on the left hand side, you have to choose the plus sign on the right hand side, and if you choose a minus sign on the left hand side, you have to choose a minus sign on the right hand side. So I have combined the commutator of Lz with both operators, with the plus operator, with the L plus operator and L minus operator. Both commutators have been shown in equation number 26 as a single equation. Now, if you change the order of the commuting operators, of course, then additionally a negative sign will appear, which will be multiplied on the right hand side of equation number 26 to give you equation number 27. So in equation number 26, if you change the order of the commutator on the left hand side, you have L plus minus commutating with Lz will give you, that is the commutator of L plus minus with Lz will give you minus plus H bar L plus minus. It follows directly from equation number 9.3, that is the commutator of L square with L plus minus 1 will be 0. So let me show you equation number 9.3. So this is the equation. You see that in this equation L square, the commutator for L square with the individual components of Lx, Ly or Lz will be 0. So you know that the L plus operator is represented by Lx plus iota times Ly. So the raising and the lowering operator both involve Lx and Ly variables, and with each individual Lx and Ly and Lz operators, the commutator with L square is equal to 0. So using this condition, I can directly write that the commutator of L square with L plus and L minus, that is with the raising and the lowering operator, will be equal to 0, because L plus and L minus both involve Lx plus minus iota Ly, and with both Lx and Ly individually, the commutator L square or the commutator of L square with the Lx and Ly individually are 0, which were shown in equation number 9.3. So of course, obviously, it can be written as the commutator of L square with the L plus with the raising and lowering operator will be equal to 0, as shown in equation number 28. Now, to demonstrate that L plus and L minus are the creation and the annihilation operators, or as the raising and the lowering operator respectively, we consider the operation of L plus minus operator on the azimuthal wave function FLM, which is shown in equation number 29. So L square, I am reading equation number 29, L square operating on the wave function L plus minus FLM. And since you see that from the commutator shown in equation number 28, I can change the order of these two operators. So I can take L plus minus operator on the left, and I can move the L square operator inside the bracket so that it can operate on FLM. And you know that when L square operate on F, you have the eigenvalues which is H bar square omega L. So now I can take out H bar square omega L outside this parenthesis, and I can move L plus minus inside the bracket. So I have the rightmost term in equation number 29 is H bar square omega L, and within the parenthesis I have L plus minus with FLM. So you see that what information do we get from equation number 29, that is explained over here. That is FLM is an eigenfunction of L square. That is, you know that I have used the information over here about in this particular bracket that FLM is the eigenfunction of the L square operator. So using this condition that FLM, if FLM is, or simply if F is the eigenfunction of L square, then L plus minus operating on F is also an eigenfunction of L square. So in equation number 28 and in equation, so equation number 28 and equation number 13 were used in the derivation of equation number 29. So here in this region, that is in this region where I have changed the order of the two operators, I have used the commutator shown in equation number 28, and over here where I have used the L square operating on F, giving you the eigenvalue is eigenvalue. There I have used equation number 13. So now the findings from equation number 29 is that plus minus L plus minus operating on F together is an eigenfunction of the L square operator, which is obvious from by looking on the left hand side of equation number 29 and the rightmost side of equation number 29. If you consider these two terms on the leftmost side and the rightmost side, it would be obvious to you that L plus minus with the F can be taken as an eigenfunction of the L square operator. Now, since L plus minus F is an eigenfunction of the L square, it must also be an eigenfunction of Lz. Because we have also considered previously that the eigenfunction of L square will also be the eigenfunction of Lz. So now let's operate the eigenfunction L plus minus F with by Lz on the left hand side. So here what I can do, I can take out the two operators outside the bracket and I can use the information Lz with L plus minus 1 from the previous commutator, which is its value. So Lz with L plus minus will give you this value which I have used from its commutator. From here, you know that it is a commutator relationship of Lz with L plus minus shown in equation number 26, and I can expand the left hand side of the commutator and I can use the value of Lz with L plus minus 1 from equation number 26 and I can plug in this value over here, which I have shown in this bracket. And I can send, and you know that L plus minus 1 can be taken as a common term from this parenthesis, but it will be taken common on the left hand side. So I have this term which is L plus minus 1 operator, and then I have the parenthesis contains Lz plus minus h bar, and then I have the wave function on the right hand side which is FLM. The left hand side is the same, and I am just processing the right hand side in the second step. I have moved FLM inside the parenthesis. Now you see that only Lz will operate on F, which will give you M times H bar. And then I have taken FLM back on the right hand side, common wave function on the right hand side. So now M H bar plus minus H bar is a constant term which I can take outside, which I can write it on the left hand side, and then you have L plus minus 1 operator operating on the FLM. So from equation number 13, it is obvious that F it is obvious that L plus minus operating on F together is a wave function of the Lz operator with a eigenvalue giving you m plus minus 1 h bar. That is with the inclusion of that is when it contains L plus, the eigenvalue will be m plus 1 h bar. And if you talk about L minus operator, the eigenvalue will be m minus 1. So it means that when Lz operates on L plus, it gives you the eigenvalue corresponding to the higher state. And when Lz operates on L minus, that is the lowering operator, it will give you the eigenvalue corresponding to the lower state. So m plus 1 is the eigenvalue corresponding to the upper state, that is the state above FLM, and when Lz operating on L minus, it will give you the wave function. It will give you the eigenvalue corresponding to the lowering wave function. So m plus 1 h bar is the eigenvalue corresponding to the state above the FLM, and m minus 1 times h bar is the eigenvalue corresponding to the state corresponding to one step lower state of FLM. So now it is obvious from here, which we have seen previously, that when Lz operates on F, it gives you m times h bar. But when Lz operates in the presence of the raising or the lowering operator, it raises the value, it gives you the eigenvalue corresponding to the higher states or corresponding to the lower states, depending upon you are using L plus or L minus respectively. So since it is giving you the eigenvalue corresponding to with the presence of L plus, it gives you the eigenvalue corresponding to the higher state, and when using with the L minus, the Lz operator will give you the eigenvalue corresponding to the lower state. So it means that these are the raising and the lowering operator. That is, it is raising F to its higher value. That will be FL and comma m plus 1. That is the wave function corresponding to the higher state, and with the present, that is when L minus, that is the lowering operator, will operate on FLM, it will give you a wave function FL comma m minus 1. That is the wave function corresponding to the higher and lowering state will be given by the L plus and L minus operator. So that's why L plus and L minus are respectively called the raising and the lowering operator. That is L plus minus operating on FLM is an eigenfunction of Lz with eigenvalue equal to m plus minus 1 h bar. That is, the eigenvalue is increased by plus 1 due to L plus operator and decreased by minus 1 due to L minus operator. So equation number 26 was used in the first step, and equation number 11 was used in the second step in order to derive equation number 9.30. Now, since I know that L plus and L minus 1 are the raising operator, so you see that now I can simply write down the equation number 31. That is, when L plus minus operate on FLM, you will get raised or the lowered wave function. That is, you will get f L comma m plus 1 or m minus 1. So m plus 1 is the wave function, that is FL, with m plus 1 is the wave function corresponding to the operation of L plus, and FL comma m minus 1 on the right hand side is the wave function corresponding to the L minus operator. And you see that I have NC included over here, 1 over NC, where NC is nothing but a constant of but a normalization constant. Because when we move from when we relate one wave function with the another wave function, what we need to do is that we need to write down the constant of normalization constant, so that we can normalize the probability between the two functions. here where NC is the normalization constant. So equation number 31 also implies that L plus operating on FL max. So if you have gone to the maximum value of the magnetic quantum number, which is M max, and if you multiply such a wave function by the raising operator, that will produce zero on the right hand side as shown in equation number 32, because there is no state above the M max state. Similarly, if you are operating FL with M minimum, so you have reached the wave function, which is a minimum wave function, which is FLM minimum. And if you operate this wave function with L minus, there is no state below the L minimum state. There is no state below that one. So when L minus will operate on such a state, you will get zero, as shown in equation number 33. So the results 32 and 33 follows directly from the results shown in equation number 9.30, or can also be inferred from equation number 9.31. Using equation number 9.19 and 9.20 gives the following equation. So what is 9.19 and 9.20? Here you can see 9.19, which is L plus is equal to Lx plus iota times Ly, and in equation number 20 we have L minus represented as Lx minus iota times Ly. So we are using these two equations. So using these two equations, I can simply write equation number 34A and 34B. That is L plus and L minus can be written as Lx square plus Ly square plus H bar Lz. And the second equation is Lx, L plus L minus is equal to L square minus Lz times Lz minus times H bar. You know that the left hand side of equation number 34A and 34B are the same. Of course, the right hand side are also similar, but they are written in equation number 34, the right hand side is written in the form of Lx square plus Ly square, whereas in equation number 34, the right hand side is written in the form of L square operator. But of course, both are identical and interchangeable, and also interconvertible. Similarly, I can also write the other relationships, that is L minus with L plus, can be written as like this, as shown in equation number 35A. And of course, similarly in the form of L square, I can write the same equation in 35A as shown in 35B. So you see that these are the four equations, and you see that I have shown their plus and minus signs also, because these signs will change when I write equation number 9.36. So I am writing equation number 9.36, and only where the red sign appears in equation number 34 and 35, these red signs will change in equation number 36 when I writing all those four equations. So equation number 36 is actually a representation of all those four sets of equations. Actually, these are the two equations, but have four sets. So equation number 36 is written as a combined form of equation number 34 and equation number 35. Now let's start with the following equation, because we are going to get some more useful form. So you know that this is the raising operator operating on the maximum state, eigenstate of the function f will produce 0. And if you multiply this eigen equation On the left hand side by L minus, you have this equation which is shown over here. So L minus L plus operating on FL comma M max will give you 0. So you see that now I am going to substitute the value of L minus L plus operator from equation number 9.36. So this is what I have used over here. So L minus and L plus have been expressed in the parentheses in the form of L square operator. So here I have multiplied by Lz inside. So you have L square minus Lz square minus Lz times h bar. And then of course the wave function Fl comma M max. So I can multiply this operator and this wave function can go inside each operator. That is, each operator will operate on the wave function. So you have L square operating on FLM max and Lz square operating on FLM max. And similarly, H bar Lz operating on FLM max. Now you see that I am writing their values, which I have already obtained in previous equations. So L square operating on FL M max will give you H bar square omega L. Lz square operating on FL max will give you H bar square M max square. And minus H bar Lz operating on FL M max will give you H bar square M max. And I can write this one in the simplified form as shown in equation number 37. H bar square has been taken as a common factor on the left hand side, and within the parentheses I have omega L minus M max square minus M max, and this now is a and on the right hand side I have FL comma M max is equal to 0. Now you see that the previous equations containing the FLM and the operators were in the operator form, and now this equation, which is written as a last step of equation number 37, is in the eigenvalue form. Now you see that I have again shown a red sign, a negative sign in red, because when I shall be using some other operator, then this sign will change. So the term within the parenthesis must be 0 for the equation to hold, because this is now the equation in the eigenvalue equation, and this equation will hold only, that is, equation will be equal to 0 only when the parenthesis is equal to 0, because the other terms will not be equal to 0. So I can write equation number 37 in the form that L plus, and now you see that over here, okay, this is our final result shown in equation number 37, and this result was obtained when we considered that L plus was operating on FLM max. Now I am choosing the reverse of that one, that is L minus operating on FLM minimum. So this is shown over here. So the operator L plus L minus operating on FLM minimum will again produce 0. This will lead to the following equation, similar to the equation 37. That is similar to the equation number 37. You can directly write equation number 38. And you can see that the positive sign has been shown in red in equation number 38, so that you can combine these two equations if you want. Now equation number 38, 37 and 38 give the following equations. So you equate both equations for omega L, and then you can write equation number 37 and equation number 38 in the following form. So omega L has been written from both of these equations on the left hand side. So omega L is equal to M max times M max plus 1. and also m minimum times m minimum minus 1. So you can get omega, you can solve these two equations, that is equation number 37 and 38. The both parentheses can be set equal to 0, and you can solve the value, and you can solve those two parentheses for the value of omega L, and finally you will get, you can equate those two value of omega L and you obtain equation number 39. Now you see that in order to get useful information from equation number 39, I am setting m max to be equal to capital X and m minimum to be equal to capital Y in equation number 39. Then of course equation number 39 can be written as x square plus x is equal to y square minus y, or x square minus y square plus y is equal to 0. Or you can factorize this one, will give you the first factor is x plus 1, x plus y, the x plus y times x minus y, and the factorization gives you product of x plus y and x minus y, and the other factor is plus x plus y. You can take one of the factor, that is x plus y, common, so you have now the product in the form of two factors, that is x plus y times x minus y plus 1 is equal to 0. Now you can set the two factors individually equal to 0 and reversing back their values, that's m max is equal to x and m minimum is equal to y. So if you reverse these two values over there, what you will get this value, that is m max plus m minimum times m max minus m minimum plus 1 is equal to 0. Obviously the equation, the second factor, which is m max minus m minimum plus 1 is equal to 0, is not physically accurate. So if you solve these two factors from the first factor, you have m max is equal to minus times m minimum as shown in equation number 9.41a, and the other factor is m max is equal to m minimum minus 1 as shown in part B. Of course, obviously, equation number 9.41a is a valid choice, whereas the second choice shown in part B of equation number 41 is not physical. So we are choosing equation number 41a, that is m max is equal to minus m minimum. Each application of L plus to FLM increases the eigenvalue m by plus 1. The difference of the eigenvalues, which is mx minus m minimum, must be an integer. Because you know that when L plus, that is the raising operator, operates on the azimuthal part of the wave function, it raises the value by plus 1. That is by plus 1 is the integer value. So it means that if you operate on f minimum, if you operate the L operator on FL m minimum FL comma m minimum successively, and you reach the final value, that is m max, then the difference between m max and m minimum must be an integer. So let us express this difference using equation 9.41a in the following form. So you have m max minus m minimum from equation number 4.18, which should be equal to, if you put the value of that one over there, that this should be equal to minus 2 times m minimum, because here you have used equation 9.41a, that is m max is equal to minus times m minimum, or you can substitute that m minus m minimum is equal to m max. So if you want to find out m max minus m minimum, you can substitute the value of m max over there from the previous equation, and you will get minus 2 times m minimum. And you know that m max minus m minimum is an integer value, so you can simply write that the integer should be equal to minus 2 times m minimum. Or you can write this one as minus m minimum is equal to integer by 2, as in equation number 42a. And you can also write them m max is equal to integer by 2 and in equation number 42b. because m max is equal to m minimum, and m minimum has been obtained as integer divided by 2. So you see that in equation number 42a and 42b, you have at least one thing, that is m minimum, that is minus m minimum, and m max are actually integer values divided by 2. So you see that from here you can infer two informations, that is m minimum are either whole integers, that is m minimum, and m maximum are whole integers, whole numbers, when the integers in equation number 42a and b are even integers. So if you put even integers in equation number 42a and 42b, you will notice that minus m minimum and m max becomes integer values, purely integer values. But if you put just integers, odd integers, replacing the integer in equation number 42a and 42b, if these integers are replaced by odd integers, then minus m minimum and m maximum will change by half integer values. So now there are two obvious choices, that is m max, that is m will change in integer values, that is whole integer values, or m, the variable m, that is the quantum number L, will either will change as with integer values or will change with half integer values. Now we have to find out that which choice, that either these integers represent even integers or odd integers. So it is required that the orbital motion of the electron, so it is required that for the orbital motion of the electron, all values of m, and particularly m max, must be integers. For this we set. So you see that here we are assuming from our previous knowledge that m must be an integer, and we shall also establish that one. But here let's take it for granted that m must be an integer. For that one, we can set m max is equal to plus L, and of course m minima is equal to minus L. So you see that these are the extreme values, that the extreme value of m max is represented by plus L, and extreme value of m minimum is represented by minus L, where L is the orbital quantum number and m is the magnetic quantum number. So you see that so far I have not talked about what is L. I have just taken L as the number only. But here and m, I have said earlier that m was the quantum magnetic quantum number. Now I am giving it a name, that L will be regarded as the orbital quantum number, and m is the magnetic quantum number, and the maximum value of the magnetic quantum number is equal to the orbital quantum number, and the minimum value of the magnetic quantum number will be equal to the minus times the orbital quantum number, as shown in equation number 43a and b. But you see that we shall also establish later in this slide that m should take even integer values, where it will be obvious that m, that the quantum number, that is the magnetic quantum number m, will only take integer values, and we shall exclude the option of half integer values which were given in equation number 42a and 42b. So only one choice from for equation number 42a and 42b will be chosen, that is these integers shown in equation number 42a and 42b will be taken as even integers, so that m, the quantum number, the magnetic quantum number L, m will take only integer values, and their maximum values will correspond to the orbital quantum number plus L and minus L respectively, as shown in equation number 43a and 43b. So you see that so far the result, we can combine our results as m, that is the magnetic quantum number m changes from m minimum to m maximum, and of course we can also write it in explicit form in its values, that m should change from a minus L value to the plus L value. So it means that the value, that is the possible values that m quantum number, that is the magnetic quantum number m will have, will be 2l plus 1 values of m. That is, there are 2l plus 1 values of m from minus l to plus l. This would only be possible when m takes integer, that is the whole number values. And you see that when we say that it has 2l plus 1 values, it means that we have also included the middle values between these two extreme values. And the middle value will, of course, will be a zero value. So it means that L will be a zero value. So L will start, L, the minimum value that L can take will be zero, which is also obvious from over here, that m takes the values from minus l to plus l, and m changes in integers. So it means that the central value will be zero. The central value of m will be zero. It is still to be established that plus minus l are integer values, and so m values, that is m, are also integer. So we need to establish that plus minus l are integer values, and also m are also integer values. We shall come back to this point after expressing the azimuthal wave function FLM in another form, writing equation 931 in the following form. You see that, let me show you equation number 931 first. You see that this is the equation 9.31. I can transform this equation in more appropriate form as shown in equation number 45. So FL with m plus minus 1 is equal to NC times L plus minus times FLM, where NC is the constant of normalization constant, which is required when you are connecting the two different wave functions in representing two different states. We need to put a normalization constant, so that when we calculate the probabilities, we can calculate accurate probabilities of finding the electron in the region covered by the azimuthal quantum number, azimuthal wave function. To find the normalization constant NC, both sides of equation 45 are integrated with appropriate limits as given on page number 5. And before that, a complex conjugate wave function f star L with plus minus 1 is multiplied as one of the options. The value of NC is found as given. So you see that you need to multiply it with the conjugate wave function, conjugate azimuthal wave function, and then you need to integrate with the limits as given in on page number 5. So let me show you page number 5. Limits on page number 5. For example, this is page number 5, and these are the limits that I have shown with the integrations over here. You can see these limits, and similarly, if we specify these limits and integrate, you can find out the constant normalization constant, which is shown in equation number 9.46. That is in equation number 46. So NC is equal to 1 over h bar times 1 over square root of L minus plus m, and another factor is L plus minus m plus 1. So you see that these are the, so you see that this is the normalization constant. NC is equal to 1 over h bar times 1 over square root of the first bracket contains L minus plus minus plus m, and the second factor contains L plus minus m plus 1. That is in equation number 9, in equation number 45, since the wave function contains m plus minus 1, with when it contains m plus 1, you will choose the upper signs, and when it contains m minus 1, that is the lower sign, with the lower sign on the wave function, you will choose the lower signs over there. And then of course, if you plug in these values of NC in equation number 45, then of course correct probabilities can be calculated. So FLM will be operated by L plus minus 1 to construct different eigenfunctions. But before that, it is desirable to express Lx, Ly, Lz in spherical coordinates. So you see that if we want to construct different eigenfunctions of our problem, what we need to do is that we need to operate the azimuthal part of the wave function by these raising and lowering operator, that is by L plus and L minus. Sometimes it is desirable to represent these operators L plus minus operator, that is the raising operator, and the lowering operator in the azimuth in the spherical polar coordinates. For that one, first we need to express Lx operator, Ly operator, and Lz operator in the spherical polar coordinates. So you see that I am just writing Lz operator in spherical polar coordinates as h bar over iota times x times partial derivative with respect to y minus y and the partial derivative with respect to x. And of course, for derivative, we have h bar divided by I times curly over curly 5 as shown in equation number 47. Similarly, the other operators, I am not going to prove this one, and you can also write a conversion equations between the Cartesian coordinates and between the spherical polar coordinates, and then you can work out very easily the this operator. Similarly, I can write the Lx and L operators as given in equation number 48 and 49. So you have Lx and Ly and Lz in the in the spherical polar coordinates, and you can use the value of L and Lx and Ly in order to express the raising and lowering operator, that's L plus operator and L minus operator in spherical polar coordinates. So you can express the L raising and lowering operator in the spherical polar coordinates. And then you can operate the wave function, the azimuthal part of the wave function, by the raising and the lowering operator to generate different wave functions of the problem. So now in equation number 50, I am writing the wave function, azimuthal wave function FLM, as e to the power iota m times e to the power iota m phi and times FLM of theta. So you see that here I am introducing small f as the wave function, as the azimuthal part of the wave function. That is as the wave function which is the theta dependent. So you see that I am now assuming that FLM, capital F, can be splitted into the product of two wave functions. One is phi dependent and the other is theta dependent. The phi dependent part I have taken is e to the power iota m phi, and the theta dependent part has been taken as FLM as a theta dependent part. This small f theta dependent part can be represented as Legendre polynomial. So now you have the product, that is you have capital F as the product of e to the power iota m phi and the Legendre polynomial, associated Legendre polynomial PLM as a function of cos of theta. Now in equation number 9.50, if you make under these conditions, that is phi replaced by phi plus 2 phi in equation number 50, the azimuthal part FLM will behave as a single valued function only if m is an integer. Single valued mean that if you change this under this substitution, that is f replaced by f plus 2 pi, the value of the wave function should not change. That is, the value should be remain a single valued function, and that is only possible in the above presentation shown in equation number 50, that m is an integer. Therefore, half times multiples of integer choice must be excluded from equation number 9.42b. So now the equation number 9.42b can be modified as, that is m max can be written as m integer divided by 2. That is m max can only have integer values. That is the variable m can have only integer values. You see that here, this is the point that we have found that m will take only integer values, and that comes from, and this information comes only when we write the wave function in the form given by equation number 50. That is, the azimuthal part of the wave function capital F will be split into two part. One is phi dependent, the other is theta dependent, and the phi dependent part should have a form e to the power iota m times phi. This will give you the information that m will take only integer values. So thus all m values in the range, that is m is greater than equal to m minimum is less than equal to m maximum, are integer values. And L values are also integers, of course, because M is bounded. M has a maximum value and a minimum value which were set equal to plus L and minus L in one of the previous slide. Then of course we can also write that M is greater than equal to minus L, is less than equal to plus L, and both and the L values are also integer values. So M values are the integer values, L values are also the integer values. So it is still to be established that what are the possible integer values of L. That is, what is the initial value of L and what is its final value. This is still to be determined. The range of values of L will be determined in the next slide. Let us construct lowering operator using Lx and Ly operator from equation number 48 and 49. You see that previously I have expressed Lx and Ly using this spherical polar coordinates, and now I am using their values from equation number 48 and 49 in this equation to find out the L minus operator. So L minus, that is the lowering operator, is defined as Lx minus iota times Ly, substituting the values of Lx and Ly from equation number 48 and 14 number 9 and simplifying these results. I am finally reaching equation number 52. The results are very simple. You can calculate these results by yourself. And finally, I have L minus operator is equal to minus h bar e to the power minus iota phi times curly partial derivative with respect to theta minus iota cot of theta times the partial derivative with respect to phi, as shown in equation number 52. Now consider L minus. When L minus operates on FLM minimum, it will produce a zero state because this is the minimum state. I have already discussed that. Now I am going to replace M minimum with its value, which is minus L. And now I have this wave function L minus operating on F L comma minus L, where FL comma minus L from equation number 50 can be written as e to the power minus iota L times phi, and then the theta dependent part is f small f L comma minus L as a function of theta is equal to 0. You can use equation number 50. You can replace the value of m by minus L and you will get this equation. So you see that now you can put the value of L minus lowering operator from equation number 52, which is this value. And of course, it is operating on over here on these on the e to the power minus iota L phi and operating on the small f L minus L as a function of theta. So you see that we can easily operate e to the power minus iota L phi can be operated. You send these two functions one by one. You can send e to the power minus iota L phi inside the parenthesis, where where it will be operated by partial over partial 5, that is e to the power minus iota L phi. When sent inside, when moved inside the bracket, it will be operated by the partial derivative with respect to 5, and of course the value is shown in the parenthesis. And then of course you can take common terms in the as shown on the right hand side, shown in red on the left hand side of the parenthesis, shown in red, that is minus h bar e to the power minus iota phi, and then e to the power minus iota L phi has been moved on the left hand side. These were the common factors in the above parenthesis, and we can remove these one because the right hand side equation is equal to 0. So now the equation that we have is the partial derivative with respect to theta minus L times cot of theta, and this will be operating on the theta dependent part of the wave function, which is a small f L minus L comma minus L. So you can write this equation now in the exact differential form, and you have d f over d theta is equal to L cot of theta times f. And now you can move the variables on common variables on one side. So you have df over f is equal to L cot of theta d theta. Now you see that you can integrate this equation very easily. The integration of the terms, that is df over f, will be log of f. And on the right hand side, you can write cotangent theta as cos theta over sine theta, and the sine has a derivative which is equal to cos of theta. So again, you can write the cos theta d theta term as log of sine theta. So the right hand side is L, and the integral gives you log of sine theta and plus constant C1 as the constant of integration. So you can raise this equation by the exponent. So you can raise e to the power log of f, and the right hand side can also be raised e to the power L into log of sine of theta plus constant of integration, as shown in the last step. Now you see that you can expand exponential term, that is you can write it as e to the power c1, and the other factor can be written as e to the power log of sine of theta raised to the power L. And you see that here e to the power c1 can be replaced with another constant represented as c. E to the power c1 is represented by capital C, and you see that this exponential will cancel out the logarithmic function, and you will have sine of theta raised to the power L. So you have now fl comma minus L as a function of theta is equal to c times sine of theta raised to the power L, as shown in equation number 9.53. So you see that you have obtained an expression which is a theta dependent, that is theta dependent part of the wave function has been shown in equation number 5.3 in its explicit form. But the constant of normalization, constant C, is still unknown. The constant C is found through the normalization condition given below. That is, you can apply this condition for the normalization, and you can obtain the value of C, which gives you capital C is equal to 1 over 4 pi square root of 4 pi times square root of 2L plus 1, the factorial of 2L plus 1 divided by 2 raised to power L and the factorial of L. So this is the value of the normalization constant that you can obtain using the condition shown in equation number 54. where phi ranges from 0 to 2 pi and theta ranges from 0 to pi. I think that in one of the previous slides I have mistakenly given you the wrong limit of theta, but here you can see that the explicit form of these limits are given. So phi can be given from 0 to 2 pi and theta will change from 0 to pi. And after solving the integral given in 54, you will obtain the constant of integration shown as C is equal to shown as 1 over square root of 4 pi and then multiplied by the square root of the factorial of 2l plus 1 in the numerator and divided by the 2 raised to the power l and the factorial of l. So all the angular momentum eigenfunction can be constructed from this. So the raising operator operating on the full form of the azimuthal wave function f capital FLM, and on the right hand side we have h bar e to the power iota phi, and the parenthesis contains curly over curly theta minus m times cot of theta operating on capital FLM. So equation number 56 can be used to generate all the higher states of the FLM wave function, where FLM has been defined in equation number 50. So from equation number 50, you can plug in the value of FLM in equation number 56, and you can operate the same way that I have shown the operation regarding the derivation of equation number 53, and you will come out other wave functions also. So all the wave functions can be generated, and of course the corresponding eigenvalues too. Now you see that what we have done so far, we have learned that m, that is the magnetic quantum number, has integer values, and that it is bounded by the two values of it ranges from minus L to plus L, and L, which is the orbital quantum number, has also integer value. So m will be integer values bounded by from minus L to plus L, that is the magnetic quantum number L changes in integers and has a total of 2l plus 1 values, and m also includes 0 value, and of course the L determines the upper and lower bounds for the magnetic quantum number m. L are also integer values. So far we have established the two quantum numbers, that is the magnetic quantum number and the orbital quantum number. When we were solving the azimuthal part of the hydrogen atom, we find that we have two quantum numbers, magnetic quantum number and the orbital quantum number, and we have also relationship between them. And we have also found that what are the values of m and what are the ranges of m and how the two quantum numbers are related with each other. Now I am going, you see that in equation number 50, let me show you equation number 50 first. You can see that I have also this small FLM, which is the theta dependent part of the wave function, has been represented by the associated Legendre polynomial represented by capital P with the two subscripts L and M, and as a function of cos of theta. This associated Legendre polynomial appears in the derivation of the differential equations related with the hydrogen atom or with the central potential, where you know that L is the orbital quantum number, M is the magnetic quantum number. So now let's talk about this Legendre polynomial and some relationships that govern the properties of these Legendre polynomials. When M is not present, it is regarded as the Legendre polynomial, and when M is present, it is regarded as the associated Legendre polynomial. So this is the Rodriguez formula for the Legendre polynomial. Rodriguez formula for Legendre polynomial is shown in equation number 57. That is PL as a function of x is equal to 1 over 2 to the power L times L factorial, and then the derivative to the power L, that is d over dx raised to the power L, operating on x square minus 1 raised to the power L, where you can choose x is equal to cos of theta when dealing with the hydrogen atom. So you see that this is the relationship given by the Rodriguez as for the Legendre polynomial. Now for the associated Legendre polynomial, you have another relationship. You know that m is present in the associated Legendre polynomial. Now you have PLM as a function of x is equal to minus m raised to power n. And then you have 1 minus x square raised to power m by 2. And then you have the derivatives raised to power m, that is dm over dxm, operating on PL of x. Again, you know that m mod is less than equal to L from our previous knowledge, and also from this is the condition of this relationship, that m mod should be less than equal to L. So you see that we can also find out that m is bounded, that is the mod of m is bounded by the value of L. If you want to solve this differential equation, so this is the condition. This condition we have also derived independently, but now this equation also appear explicitly when we need to solve equations, these differential equations. But you know that you can substitute the value of L, the value of PL of x from equation number 57 into PL of x in equation number 58. The full form of the associated Legendre polynomial given by Rodriguez is shown in equation number 59. So you have PLM as a function of x is equal to minus 1 raised to power m divided by 2 raised to power L times factorial of L. And then we have a term which is 1 minus x square raised to power m by 2. And then we have the derivative d over dx raised to power L plus, that is d over dx. This derivative occurs L plus m times. That is the derivative of this order is L plus m, and then it is operating on the term which is x square minus 1 raised to power L. So for the hydrogen atom, you can simply replace x by cos of theta, and the simplified result is shown in equation number 60. So this polynomial, associated Legendre polynomial for the case of hydrogen atom, is shown in equation number 60. So P and M of cos of theta is equal to minus 1 raised to power m divided by 2 raised to power L and times L factorial multiplied by the sine of theta raised to power m and multiplied by the L plus mth order derivative of d over d cos of theta and operating on cos square theta minus 1 raised to power L. Now we are going to give some results. You know that we need to calculate these polynomials, that is Legendre polynomials, as shown in equation number 50, that these polynomials are required, as you can see in equation number 50. If you manually wanted to calculate the value of capital F, that is the azimuthal wave function of the hydrogen atom, you need to plug in the value of L, the associated Legendre polynomial in equation number 50. And if you want to put these values over there, what you need to do is that you need to substitute their values over there in the tabular form. So if you have the values of PLM, the Legendre polynomial in tabular form is required, and you can calculate those tables by yourself, but I am going to give you the table for these values over here. So summation or the power series formula for the Legendre polynomial is also given over here. So PL as a function of x is equal to 1 over 2 raised to power L, and then the summation over the variable k going from k is equal to 0 to k mod of L by 2, and then the summation argument is minus 1 raised to power k. This is LK, this is LCK, that is the same variable that appears in the expansion formula of the binomial series, and the other expansion is 2L minus 2K and L, the same type of variables, which is called NCR variables. And then you have x raised to power L minus 2K. So this is the power series formula. You can plug in these values of L, and you can plug in the values of L and the value of x, and you can calculate this polynomial, which is the Legendre polynomial. So I have substituted the value of a in terms of x and cos of theta. I have given some values for the values of L. That is when L on the left column, I have given the value of L 0, 1, 2, 3, and I have shown the value of PL of x in the second column. I have also shown the values of PL of cos of theta in the third column. So you can see, you can also work out the other, and these tables are also available on the internet resources. You can without calculating, you can consult those tables, and you can find out the value of these Legendre polynomials, and you can use, you can construct the overall azimuthal wave function of the hydrogen atom. There is another very useful relationship. You see that I have given a relationship in equation number 61A, and you see that this equation, this relationship is only valid for the Legendre polynomial, because it depends only on the variable L. But you see that in the case of associated Legendre polynomial, a similar relationship is given, which is shown in equation number 61B. So here you can see that I have a PLM as a function of x, which is equal to 1 minus x square raised to power m by 2 divided by 2 raised to power L, and then you have the summation going from k is equal to 0 to the value L minus 1 divided by 2, the mod of this one, and the argument of this summation contains minus 1 raised to power k. This is LK, similar to NCR variable used in binomial series expansion. Similarly, you have 2L minus 2K, and at the bottom variable is L, and then you have L minus 2K, the factorial of L minus 2K divided by the factorial of L minus M minus 2K, and the x, you have x variable raised to power L minus M minus 2K as shown in equation number 61B. So you can use this expression, which is the power series formula, to calculate the different values of P and M as a function of x. So you see that I have shown these values over here. That is L. The values of L are listed in the leftmost column. The next column contains the values of M. The third column contains the value of a PLM as a function of x, that is the associated Legendre polynomial as a function of x, and the fourth column contains the associated Legendre polynomial as a function of cos of theta, that is meant for the calculation of hydrogen atom. You see that for each value of L, M takes the value from 0 to 1. That is, when L is equal to 1, M will take two values, 0 and 1. And when L is equal to 2, M will take M takes values 0, plus minus 1, plus minus 2. So again, when L is equal to 1, M takes three values, 0 and plus minus 1. And when L is equal to 2, M takes three values. M takes five values, 0, plus minus 1, plus minus 2. But in the column under the values of a magnetic quantum number M, I have shown only the positive values. But the negative values also exist, but I have just shown the result for the positive values. So P and M that is the associated legendary polynomial in the third column, the values are listed, and for the hydrogen atom, the associated legendary polynomial values are listed in the fourth column. Now we are talking about the spherical harmonics of hydrogen atom. You see that before that we have using, let me show you equation number 50 first. Here you can see that I have FLM on the left hand side, and on the right hand side I have this dependence. This FLM can also be represented in terms of the spherical harmonics. The complete form of the spherical harmonics can be given as shown over here. The wave function of hydrogen atom is separated into the radial and the angular part. The angular part of the wave function is described by the spherical harmonics represented by YLM and depending upon two variables theta and phi. And you see that it is actually the same function capital F that we have been using. But now we are replacing that capital value of capital F with the inclusion of the normalization constant. The full form of the angular part of the wave function used in the hydrogen atom is given in equation number 62. So YLM as a function of theta and phi is equal to -1 raised to power m. Then you have a square root containing 2l plus 1 in the numerator and 4 pi in the denominator. And then you will have factorial of L minus 1 divided by the factorial of L plus m. And then you are going to multiply this term with PLM as a function of cos of theta. And then you have e to the power iota m phi. So you see that this is a full form of the angular part of the wave function known as spherical harmonics used for the hydrogen atom. Now you see that I am going to give you some values for this spherical harmonics. These are listed over here. Only selected values are given. For y00, the value is given over here. Similarly for y10, for y1 plus minus 1. So you know that when L is equal to 1, the m values will be plus minus 1. So both values are given. So when y is equal to 2, the only values of m will be 0. And the other two values will be y2 plus minus 1 and plus minus 2. So when L is equal to 2, that is when the orbital quantum number is 2, the 5 values of m will be 0, plus minus 1, plus minus 2. And these values have been shown also. So you see that the full form and these values you see that are shown for the hydrogen atom. And these are the azimuthal part or the angular wave function used for the hydrogen atom known as the spherical harmonics. So you see that the study of the hydrogen atom is still not complete. We have only solved for the spherical part of the hydrogen atom. We also need to study the different shapes in which the electrons move. That is, the orbital shapes of the hydrogen will also be studied in the next slide of this part. That is in slide number 9b. I shall be presenting different parts representing the probabilities of the existence of the electron in different orbitals will be presented. And that will be presented in the slide 9b. And of course, thereafter I shall be solving the radial part of the hydrogen atom. So then that will be a complete picture of the hydrogen atom will be presented. And you see that the quantum mechanical treatment is essential. Otherwise, I cannot derive these quantities. Though some of them can be derived classically, but not completely by the complete solution will be only given by quantum mechanical treatment. So this is the end of slide number 9A of the course on atomic and molecular physics.